I'm the team lead, Jason Sadie. We have Austin Urban and Luis Pinto. Our advisor is Professor Diane Castellino, and our sponsor is Dr. Paul Fortier. We were given the task of creating a 3D first responders localization unit, which would find targets in 3 dimensions. So we find their X, Y, and their Z coordinates. It would essentially save first responders time in finding targets inside of a building. And we would create a monitoring device that would allow our targets to be found on phone, on the Android phone, and on the command center. We would display this, in the event of emergency. They could find it very quickly and easily. And I'm going to hand it off to Lewis to give our.
Good morning. So we have a couple of customer requirements. So our data needs to be exact and repeatable, and we have to identify and locate targets inside of the building within the 3 dimensions, X, Y, and Z, as well as inventory first responders location. We needed to design them in order to be receptive and easy to use, and the full access is only granted for the first responders. Now we proceed to the engineering requirements. For the accuracy, the location of the target and responder needs to be narrowed down 6 feet within the Z-axis and 25 feet within the X and Y axis. This is due to the reason because it's more important to us to know where the targets are located on the floors. This is due to the reason we need to know the floor level that the targets are located rather than where the targets are located inside of the building. And use repeatability within the same range. We need to make sure we have the correct values. The measurements for shrouds and accuracy. We have to capturize and process location data to export X and Y, Z coordinates. We have to monitor first responders locations using phone sensor data, and this is used to monitor on a map view using similar location method for the targets as well. We need to program the application in order to utilize the building sensor that comes with the phone. And as I mentioned before, the only first responder to have full view of the app because we need to protect the target's information. Not everyone can know the target's information, but first responders.
Thank you. So 2D location can be found using cell tower triangulation or GPS. We needed to get the 3rd dimension, and that was really our task. We additionally, at first were thinking of using RF antennas to transmit and receive signals to phones, possibly mounting 3 on the ground around the building, and then flying a drone with 1 on top to give us signal diversity and try and triangulate ourselves. But our biggest obstacle was multipath propagation and cell identity. And then we looked at some more accurate measures, and that was Wi-Fi triangulation. And RFID technology, but that would have been not as fast to implement. The targets would have to carry a tag if they use the RFID. But we were looking into ultra wideband and using like a cell phone to kind of battery assist the tag, the passive tag. But we ultimately didn't think that was going to be very quick to implement on the scene in the event of emergency. Same with the Wi-Fi locations. We would have used cell signal strength or Wi-Fi signal strength and MAC addresses to triangulate, but then ultimately we would have needed IT assistance. Then we looked into accelerometers, pairing that with the gyroscope, and taking derivatives. We would have been able to try and work that out, but we also saw a lot of inaccuracies. Ultimately, we settled on barometers. Barometers were able to take relative pressure, and using the 2 pressure points, we were able to find changes in pressure and convert that to height, and then sum those up to take us into pretty much a summation formula, which allowed us to keep relative height from our location. And a big something that really drew us to this idea was that most people have their phones on them at all times. So, you know, the one thing that you always have on you is your phone. So we really like this idea. And we thought that we could filter out, one of the biggest issues was drift. We thought we could filter this out. So I'm going to hand it off to Austin, who did a lot of our preliminary testing.
So what we ended up doing when we first started this is we downloaded an app off of the market that was already available. It was called Sensor Play. We used it on an iPhone 7, and we used this app to gather some preliminary data and try to get a wraparound of what we were getting into and the factors we would have had to deal with. And we could see from the early stages that calculating relative altitude was a very inaccurate measurement, and it had an inaccuracy about plus or minus 22 meters. But the changes inside of the pressure sensors, if you look at just the relative changes, they were plus or minus 1 meter. So the accuracy was relatively high in that aspect. So we had to develop a function to monitor the change inside the sensors rather than the change based on a fixed point such as sea level. The accuracy was greatly increased when we started looking at the changes based on itself, and that was a key thing that we had to incorporate in a lot of our next steps. And these are some figures that we found when we were doing our research, and we were able to see that what we found was backed up by some other people's data too, and about how the relative accuracy is a lot higher than its absolute accuracy. This is some of the other data. That same app allowed us to record a bunch of different functions, and we started processing some stuff. The purple line that is up there was the rough data that we were given, and it is kind of all over the place, and there's a lot of drift in there, and it goes up and down through floors, and eventually through the sample, by the time it was done, it had drifted about a whole floor level, about the period of about a half hour, 45 minutes. And the blue line is what we came up with for a function to try and correct that drift and make it more accurate for what we needed to do.
All right, and then we had to develop an app which allowed us to take this barometer data and for our first responders to be able to view it. And on the left, we have how we're writing to our database, and that's using the username that they register with and their full name, and it would record their height, their latitude, their longitude, the time of their height change. So every time their height changes, that time is updated. So if you were to look at it on your phone, see that person was in that latitude, longitude, and their height, you would also know what time that height was recorded. So they're not looking for people at all times. And then also the time of reference is once they walk into that building and hit start. So, and then on the right we have our authentication. That's just the registration. That's how they would be able to sign into our app. And this is a snippet of our Android Studios code. This is specific to our pressure sensor. We were able to have an accuracy change function. This actually checks the accuracy of the sensor, and I've coded it so that it's only going to work when it's medium to high accuracy, and on sensor change, it uses an if statement it only writes that new pressure value if it's high accuracy or medium accuracy. Otherwise, it will give us a little message saying that's inaccurate. And then we have two important variables. It's delta time and delta pressure. Delta time is how often we're checking our new pressure to our old pressure. And then we have delta pressure, which is taking that new pressure and that old pressure and then comparing them. The absolute value of the new minus the old has to be above a certain variable for us to even consider it to be a real change rather than noise. So it's somewhat of a low pass filter. And then at the bottom here we have the actual equation that we're using to convert the pressure to height, which is our gas constant times the temperature, which is in Kelvin, times the the ratio of the new pressure to old pressure over the negative molar mass of air times gravitational acceleration. That will give us relative accurate height. So, this is also snippets of our application. On the top left, we have the sign-in page. In the top middle, we have our registration. Top right is the target monitoring page. The bottom left is the admin monitoring page, and at the same time, it's also monitoring the admin's height at the same time while they're completed. And then the bottom, middle, and right, I'm going to hand off to Austin. This is the command center that he built.
So in addition to the app that we built, we also designed a MATLAB script that would take all the information that was passed to the database, and it would allow us to search it and plot it inside of a certain radius, and it would show all the points in 3 dimensions with a satellite image of where they are, and you can zoom in and out on it, and you can scroll around with it to give like a command center view if you had a laptop or some sort of desktop monitor to look at rather than just a cell phone. So it would give you a better idea of the grand scale of everything that was going on inside of that building, or anything inside of the given area that you search.
All right, and so for every single one of our engineering requirements, we needed a test to verify. So for our accuracy, our repeatability, and our drift tests, we actually added drift as we were testing accuracy. We noticed that the more accurate we were, the more we were drifting, and vice versa. The more we tried to filter out the drift, the less accurate we were. So there was a trade-off. So we made tests that would, make sure that we were being accurate and respecting the balance. We were also locating targets using the XY as well as one of our tests, and doing the same thing for the first responders and displaying them on a map view. And we were also making sure that we were only allowing admins the information of our targets. We had to respect their privacy and not have it open for public. So this was just one of our test logs. We tested in the Clarity Carney library. We're also going to have a demo later showing this, but this was a different scenario. This was a different time where we tested, and we started at 4 feet. I started the summation at 3 feet, because typically when you have your phone on you, it's in your pocket or your hand, and that's 3 feet off the ground. So we started testing. It was at 4 feet. We walked all 4 flights of stairs up, and we were at 43 feet. And then we walked all the way back down. We ended at 5. So every single time we noticed it incremented by 9 to 11 feet. So it was pretty spot on. And that was using the delta time of 2,000 milliseconds and delta pressure of 0.01. And this was using this test 2 was testing the XY axis. And every single time we walked into a new building, we would test. It was spot on, except for one time, I think, when we tried to open a campus center up in Ring Road. So it has some tweaks, and there could be other ways to code it that we could request updates or check the accuracy. But it was spot on about 80% of the time. And then these were tests for drift. I noticed that when we increased delta time, we also were far more accurate at filtering drift. certain ways that there were certain codes that we used to check between drift and accuracy, and the final column on this column over here, we used the same code that was extremely accurate, and we were able to limit the drift for an hour and a half before we finally got out of that 6-foot range. So that was impressive. Although there could be secondary methods to filtering this drift. But all in all, our testing summary, we failed the drift test. Everything else was really a pass, except for as well the handheld admin page. We had some trouble locating our targets on, because we had to code in the actual node that we were looking for, and each one was specific to the user. I actually thought of a way yesterday. I think we could have changed it, but if we had more time, I think we could have worked on this and found this to pass. Our schedule, we grossly underestimated how long it would take, especially the coding. I thought it'd be 30 hours of code total, but debugging alone probably took about 60. So there was a lot of a big learning curve. As well as the sorting and processing data, that also was a very, very long process. That was making the command center and figuring out the calibration, the testing variables also took a long time. And then we have a demo.
So now we're going to present a demo where we did some tests. The test took place in the school library, where we went down the staircase and we.
Right, so we're looking at the Carnegie Library on the staircase number 3. Where
It's also, you can notice that
5 floors
as I move, the command center shows the movement.
For our relative height, it actually started at 3, but it's drifting a little bit. It's back up. It's just jumping between the two. But we're gonna go walk up all 5 floors, and I'll read the values as they change per floor. So right now we're at 8 feet. Right now we're at 14 feet, 15 feet. It's actually back down to 13.
I think I have bad service, but it'll jump.
This is on floor 2.
It's just that it's there. I think right now it's spot on at this point.
Now we're at 23 feet, 24 feet. This is on floor 3. So on the 4th floor, we are currently at 33 feet, which is about 30 feet greater than we started at. Which makes sense because we've increased 3 floors since. Now we're at 5th floor, and we're at 42 feet. We've gone up 4 floors. Each floor is roughly 10 feet, so it's pretty accurate. Now we're just going to walk back down. So then 41, 40, 39, 38, 37. It's got a slight delay, so we wait a second before we read it. 33 feet. 2. We started at 3 feet, it drifted, it's now 1 foot, so it had 2 feet of drift. And we're back on floor 1. And that concludes our test. Thank you.
All right, and so I was the only one who had an Android phone at the beginning of this year. So once we started testing, we had to also ask our friends for phones, and that's when we realized that not all smartphones have barometers. That was a big thing that shocked us. It was specifically, I think it was LG. I mean, both times that we found a phone didn't have a barometer. I think it was just the LG brand. Barometers are also sensitive to external environments, so the humidity and temperature also plays a role in the pressure. So that ways of filtering that, maybe creating a second method using the accelerometer, or even some newer phones have significant motion detectors. If that was implemented as a second method, if the significant motion detector is not triggered, then it would ignore any pressure changes. That would be a secondary method of adding in a way to filter all these changes. Also, one of our biggest challenges this semester was none of us really had any Java experience coming into this, or Android Studios coding, so this was all a new task for us. So it wasn't always the most efficient functions being called, and so it was a big learning curve. But if there was future development, I think a CIS student could really take this to the next level. So, are there any questions?